Something is missing off the coast of Japan. Not a building, not a ship, an earthquake. 36 hours ago, a magnitude 7.5 ruptured the Japan Trench. The initial shaking has stopped. Tsunami advisories have been downgraded. Helicopters have finished their first damage assessment passes, and the global news cycle has already begun to move on. In a nation engineered to absorb a shock of this scale, the rhythm of society has mostly returned to normal. But in the quiet monitoring rooms of Tsukuba, the mood is not one of relief. It is something closer to unease. Because what seismologists are looking at, or rather, what they are not looking at, is a hole in the data where an entire population of earthquakes should be. Since the moment of rupture, the ground has been doing something it is not supposed to do. It has been quiet. Too quiet. The aftershocks that should be echoing downward in size are thin. The largest one recorded so far sits 2 full magnitude units below what statistical seismology demands. That is a difference of roughly 1,000 times less energy than the rulebook says we should see. The Japan Meteorological Agency has already started a 132-hour countdown clock, and they are openly naming precedents like Tohoku 2011 and Kamchatka 2025 that began exactly like this. Tonight, we walk through what this silence actually means and why the next 3 days may be the most important window in Pacific seismology this decade. The question is no longer how hard the ground shook. The question is, why, after such a violent rupture, has the Earth gone so silent? Welcome to Plasma Pulse. If you genuinely enjoy our investigative deep dives into the anomalies of our planet, hit like and subscribe. This story has 132 hours left on the clock, and we will be here tracking every one of them. Tell us in the comments where you are watching from tonight, and consider this. 15 years after 2011, Japan poured billions into seawalls and sirens. The systems worked. The people ran. And yet, with every sensor pointed at this fault, no one can tell you if this silence means the danger is over, or if the real one is still coming. Did we learn enough? Let's get into the data. We are now 36 hours past rupture. The initial violent shaking has subsided, and the tsunami advisories along the Sanriku coast have been downgraded. Across the country, the news cycle has already begun to move on as helicopters return from their damage assessment passes. In Japan, a magnitude 7.5 is undoubtedly terrible, but it is not unprecedented. This is a nation that has engineered its very foundation to survive such events. And for the most part, it did. Buildings swayed and held, trains stopped and restarted, and the hardened rhythm of Japanese society absorbed the shock. But in a small, quiet room in Tsukuba, where seismologists watch waveforms scroll across their monitors, the mood is far from relief. It is a state of profound unease. They are looking at a hole in the data, a missing population of earthquakes that, by every statistical law, should be populating the record right now. To understand why these experts are unsettled, we have to look at the technical scene. The Japan Meteorological Agency, JMA, recorded this event at magnitude 7.5, while the USGS, monitoring from across the world, logged it at 7.4. While a 1/10 difference might seem like an accounting error, it is significant. The JMA magnitude is calibrated specifically for the unique geometry of the Japan Trench using a dense network of sensors located directly above the fault. For events here, the JMA number is the gold standard. We are treating this as a 7.5, a massive, significant earthquake that should be followed by an aftershock sequence with a very specific, predictable shape. However, the Earth has failed to deliver that shape. The first rule that has been shattered is Bath's law. This principle states that the largest aftershock in a sequence is typically about 1.2 magnitude units smaller than the main shock itself. This isn't just a guess. It is a statistical regularity observed across tens of thousands of sequences for over half a century. The expectation. For a magnitude 7.5, Bath's law predicts a largest aftershock somewhere around magnitude 6.3. The reality. In the 36 hours since the rupture, Japan has recorded a largest aftershock of only magnitude 5.4. This 2.1 magnitude gap is not a minor deviation. Because the earthquake magnitude scale is logarithmic, a 2-unit difference represents a factor of 1,000 in energy release. This means the largest aftershock so far has released only 1/1000th of the energy that statistical seismology demands. The anomaly deepens when we apply the Gutenberg-Richter distribution, which describes the waterfall effect of earthquakes cascading into smaller and smaller pools. Statistically, for every magnitude 5, you expect roughly 100 magnitude 4s. Right now, off the coast of Iwate, that cascade is thin. The hundreds of small earthquakes that should be filling the record are coming in by the dozens. In Tsukuba, seismologists have a dry, bureaucratic word for this: a deficit. But beneath that word lies a visceral feeling that something is fundamentally wrong. The question remains, is this silence the sound of a fault that has finished its work? Or is it the heavy, breathless pause before an even larger rupture? Before we follow the path toward a potential catastrophe, we must address a critical question. Is this deficit a physical reality, or is it merely an illusion of our instruments? Every earthquake catalog in the world is inherently incomplete. The smaller the earthquake, the easier it is for its faint signal to be swallowed by the background noise of the planet. While Japan's land-based seismic network is the most sophisticated on Earth, the Japan Trench is located 100 to 200 kilometers out to sea. Monitoring it requires a mix of onshore stations straining to hear across the distance and offshore seafloor instruments like the SNET system. Even with these advanced underwater sensors, the detection floor, what seismologists call the magnitude of completeness, MC, is significantly higher offshore than on land. Furthermore, during the first few days after a major event, the MC rises. The ground is still ringing from the main rupture, causing smaller seismic waveforms to overlap and disappear within the larger ones. It is possible that the hundreds of missing aftershocks are simply hidden in the cacophony. However, modern analysts are not just squinting at monitors. They are using automated detection and machine learning systems specifically designed to pick out weak events from noisy backgrounds. Even after accounting for these biases and waiting for the catalog backlog to process, the deficit persists. The experts watching the Japan Trench tonight are increasingly convinced that the silence is not a technical glitch. It is a signal. We are currently standing at a crossroads where two competing explanations fit the data perfectly, yet they lead to vastly different outcomes. Model A, the efficient rupture, the optimistic path. This model suggests the magnitude 7.5 was a clean break. It released the built-up stress so thoroughly that there is very little residual strain left to drive an aftershock sequence. In this reading, the silence is not a warning, but a sign that the fault has finished its sentence and the system is stabilizing. Model B, the stress transfer, the quiet asperity. Hypothesis. This is the scenario that keeps seismologists awake. It proposes that the rupture was incomplete, breaking only a small asperity, a stuck patch on the fault, while leaving a larger adjacent patch intact. Instead of releasing the energy, the M7.5 redistributed it. The next 72 hours represent the separation zone, where these two models will finally diverge. To understand which path the Earth has chosen, seismologists are tracking three specific diagnostic signals. Signal 1. The arrival of a magnitude 6.0 aftershock. Paradoxically, if a large aftershock occurs within the original rupture zone, it would be a sign for relief. It would mean the fault is finally behaving according to Bath's law, resolving its residual stress in a predictable way. Signal 2. Spatial migration. This is the most critical red flag. If seismic activity begins to drift along the trench or cluster in new, previously quiet locations, it is a clear signature of stress transfer. This burning fuse would indicate that the M7.5 was merely a precursor to a much larger failure. Signal 3. Continued silence. This is the most ambiguous and haunting outcome. If the countdown clock hits 0 without any of the above signals, the mystery remains unresolved. It leaves the anomaly as a statistical ghost, a sequence that defied the rules but never provided an answer. As we move deeper into this 132-hour window, the ground itself holds all the cards. We are not just watching an experiment, we are inside of it. There is a specific reason the Japan Meteorological Agency was willing to issue a Megaquake advisory within hours of this M7.5 event. It is not merely because the numbers slightly exceeded a statistical threshold. It is because the international seismological community still carries the weight of two sequences from the last 15 years that started exactly like this. The agency and its scientists are no longer in the mood to be surprised. The first precedent is the one every Japanese seismologist carries in the back of their mind: the Tohoku sequence of March 2011. On March 9th of that year, a magnitude 7.3 earthquake occurred off the coast of northeastern Japan in roughly the same tectonic setting as the event we are discussing tonight. At the time, it was treated as a significant but manageable earthquake. There were quiet conversations among scientists about whether it could be a foreshock pattern, but those concerns never reached the general public. There was no public advisory mechanism like the one JMA operates now, and the institutional structure of the time effectively kept that unease trapped inside the offices where it was felt. 2 days later, on March 11th, the Pacific Plate failed catastrophically. The resulting M9.1 earthquake and tsunami killed nearly 20,000 people and triggered the Fukushima nuclear disaster. The March 9th event was only recognized as a foreshock after the main shock arrived and rewrote the interpretation of everything that had come before. The second precedent is even more recent and perhaps more relevant to the JMA's current posture: the Kamchatka sequence of July 2025. Located at the northern end of the Ring of Fire along the same megathrust system, a magnitude 7.4 earthquake struck the region. Much like our current situation, it produced an aftershock sequence that initially looked manageable, but was followed by days of unusual quiet. Then, days later, a magnitude 8.8 earthquake ruptured a much larger section of the subduction zone. In terms of energy, it was the largest earthquake of the 21st century at that point. Once again, the smaller event was only granted the title of foreshock, when history was forced to rewrite itself. These two cases define the left edge of the probability distribution the JMA is currently navigating. They serve as a grim reminder that foreshock is not a category defined in real time. It is a label given by the future. The Megaquake advisory currently active, with approximately 132 hours left on the clock, is the institutional response to the silence of 2011. It is a deliberate admission that uncertainty has consequences. It is vital to understand what this advisory is and, more importantly, what it is not. It is not a prediction that a larger earthquake will occur, nor is it a statement that one is likely. Instead, it is a probability shift. The protocol is triggered automatically when specific conditions are met, specifically a magnitude 7.0 or greater event in a zone of elevated concern. This automation ensures that the communication is not a judgment call made by humans under political pressure, but a transparent statement of risk. The JMA is walking a tightrope between taking the situation seriously and avoiding induced panic. They are asking the public to spend a few days being slightly more prepared, to know their evacuation routes and keep emergency supplies accessible without instructing them to flee. In the cold language of decision theory, the JMA's working estimate for a follow-up megaquake currently sits at roughly 1%. While 1% sounds low in everyday life, it is astronomically high compared to the background baseline. Normally, the probability of a magnitude 8 earthquake in the Japan Trench is measured in hundredths of a percent. By stating there is a 1% risk, the JMA is signaling that the occurrence of the M7.5 has multiplied the baseline risk by a factor of 20 to 100. This is a Bayesian update, a revision of belief based on new, striking evidence. When the consequence is catastrophic, measured in thousands of lives and trillions of yen, a 1% probability is not an overreaction, it is a calibration. Human risk perception often fails here, as people tend to round 1% down to 0. But in a region where the cost of being wrong is measured in coastal towns swept away, the agency has decided that the risk has shifted enough to warrant the world's attention. As we wait, the question remains: is the Earth showing us a pattern we can finally hear? Or is this just another edge of distribution event that will expire in silence? While the primary focus remains on the seismograms of the Japan Trench, other sensors across the planet have begun to register signals that, in any other week, would be dismissed as background noise. These weak signals form a secondary file that seismologists are watching with low confidence but high curiosity. One of the most debated observations comes from a monitoring station in Tomsk, Siberia, which tracks the electromagnetic environment of the Earth. Shortly before and after the M7.5 rupture, this station recorded elevated energy in a frequency band centered around 12 to 13 Hz. This is significant because it does not correspond to a canonical Schumann resonance, the standing electromagnetic waves that naturally propagate between the ground and the ionosphere. While intriguing, this is a single-station observation, which in the history of earthquake prediction is almost always categorized as local noise, perhaps wind, temperature drift, or human-generated radio traffic. Without confirmation from other stations, it remains a statistical curiosity rather than a proven precursor. Simultaneously, on the same day as the Japan Trench rupture, a magnitude 4.0 earthquake occurred at a depth of 326 kilometers beneath the Nankai Trough, 1,500 kilometers to the southwest. This event was an intraslab earthquake, occurring deep inside the subducting plate rather than on the fault interface. While physics suggests that static stress transfer across such a distance is impossible, the timing beneath a historically suspect segment of the Nankai system has added yet another layer to the week's unease. Even the sun has joined the background scenery. As the scientific debate rages in Tsukuba, the true weight of the Megaquake advisory is felt in the coastal towns of Iwate and Miyagi. For the residents who lived through the footage of 2011, this week is not a statistical exercise. It is a week of suspended normalcy. Japanese society, perhaps the most earthquake-aware on the planet, has moved into a state of calibrated vigilance. People are sleeping with their phones charged and emergency bags by the door. They are mentally retracing the routes to high ground from their workplaces and schools. The advisory has done its job. It has moved the concern from the quiet offices of scientists into the hands of the people who are most at risk. Whether the countdown clock hits zero in silence or concludes with a second rupture, the events of this week have already provided a profound lesson in the limits of human prediction. We are witnessing a mature seismological agency being honest about what it does not know. If the advisory expires without incident, it will be remembered as a successful drill, a rehearsal for a tragedy that, this time, stayed in the realm of probability. But if the quiet Asperity countercuttle proves true, this window will be seen as the moment we finally learned to listen to the Earth's silence. We remain inside the experiment. The Earth is the apparatus, the fault is the test, and the clock is the measurement window. The final hours will resolve the mystery on the Earth's schedule, not ours.